Welcome back, everybody. This is Mr. Johnson with you once again. We're in section 8.3 of our ebook on vapor and partial pressures. You've already learned a little bit about this from the College Board lecture on Dalton's law of partial pressures. That law, as you may recollect, states that the total pressure of a mixture of gases is the sum of the partial pressures of each of those gases in the mixture. And you've solved some problems on that. This will be an extension of that conversation about what vapor pressures are. Really interesting. I'll show a video at first talking about the role that atmospheric pressure and vapor pressure plays in boiling and in the boiling point of a substance. Then there's another short video giving you a visual model for what vapor pressure actually is. Then we'll apply those concepts, and then I'll solve a nice problem with you at the end using a lot of the concepts and skills we've just learned. So here comes the first of two videos.
So as we add heat to water, the water molecules begin moving faster, and some of them spread out and form a gas. We call that gas water vapor, and that's what's inside the bubbles you see. These bubbles rise to the surface, and this is what we call boiling. So we'll start with the water molecule. The red is oxygen, and the two white atoms are hydrogen. That's H2O. Water molecules are always moving. When we add heat, they move faster, and if we add enough heat, they'll spread out, and they'll form a gas. We call that gas water vapor. Note that there's nothing between the atoms here. The black is empty space. To understand why bubbles form during boiling, imagine a group of water molecules, and as you add heat, some of them spread out and form a gas, water vapor. When they spread out, they push the molecules around them away, and that forms the bubble that you see. That bubble rises to the surface. That's boiling. Remember, there are only water molecules in those bubbles. They're very energetic water molecules in the form of a gas, which we call water vapor. Boiling depends on the amount of pressure around the liquid. On Earth, the atmosphere is what creates this pressure. If we look at a cross-section of the atmosphere, only 50 kilometers has enough air for humans to breathe. The pressure also decreases as we go higher. That's because as we go higher in the atmosphere, there are fewer air molecules. Like all matter, air has mass, and gravity pulls it towards Earth. That's why the atmosphere doesn't just drift away into outer space. The weight of the air above us pushes down due to gravity, and this creates atmospheric pressure. The more air above you, the more pressure. And pressure makes it more difficult for boiling to take place. Think of it like these books. The more books, the more pressure. And the more pressure, well, eventually, it'll crush the can. When you go up a mountain, there's less air above you pushing down, and the pressure is lower. Your ears can pop, and water boils at a lower temperature than it would at sea level. So back to boiling. Boiling happens when water molecules have enough energy to spread out and to form bubbles. These bubbles rise to the surface, and they release the water vapor. Since the water vapor contains these more energetic molecules, releasing them into the air cools the water. So here we have our beaker with a bubble. If we increase the pressure, the molecules in the bubble will move closer together, and eventually they'll change back into liquid water. Alternatively, if we decrease the pressure, that makes it easier for those water molecules to spread out and form a bubble, and that's boiling. We can see this with a syringe. We push in the plunger, we increase the pressure, molecules move closer together, and the bubble becomes smaller. When we pull the plunger out, we're decreasing the pressure. That means those molecules can spread out more easily, and the bubble grows. If we pull the plunger out and decrease the pressure enough, water will start boiling. Note that the temperature doesn't change. It doesn't get hotter when it boils. It's just that there's low pressure, the molecules can spread out to form bubbles, and that's what we see happening here. Boiling is strongly influenced by the atmospheric pressure. On Earth, that pressure is created by gravity pulling air molecules down towards Earth. Those air molecules push on a liquid, and they can make it more difficult for boiling to take place. Remove the pressure, and it's easier for boiling to take place as the more energetic molecules spread out and form bubbles. Note that we haven't talked about the pressure created by molecules of water escaping the liquid. That's called vapor pressure, and the subject of the next video. We know that boiling is strongly influenced by atmospheric pressure. Pulled down by gravity, the air above us creates pressure, and that makes it difficult for bubbles to form and boiling to take place. We can think of atmospheric pressure as the collisions of air molecules against the surface of the water. That's the pressure. The more collisions, the greater the pressure. But water molecules can create pressure when they leave the liquid. As these faster moving water molecules escape, they collide with the molecules of air. This creates pressure, and we call it vapor pressure. In a way, the water molecules are pushing or colliding against the air molecules. This reduces the amount of pressure felt by the water. Back to boiling. Textbooks often state that when the vapor pressure equals the atmospheric pressure, boiling takes place. This is called the boiling point. Think of it this way. Atmospheric pressure pushes down, and that makes it difficult for the water molecules to spread out and form a bubble. But when the vapor pressure increases, molecules from the liquid escape and they push against the air molecules and effectively reduce some of the pressure. This makes it easier for the liquid molecules to spread out, form a gas, and to rise to the surface. That's boiling. We can make boiling happen by either increasing the vapor pressure or decreasing the atmospheric pressure. Either way, once the vapor pressure and the atmospheric pressure are equal, we've reached the boiling point, and boiling can begin. One last thing. Different substances have different vapor pressures, and therefore they have different boiling points. This has to do with how strongly the molecules are attracted to each other in the liquid. The more strongly they're attracted, the less the vapor pressure, and it's more difficult to boil. Therefore, the higher the boiling point.
So we'll review the key concepts from that video in a bit when we come back to our ebook, but first I want to share with you one more short video on what vapor pressure is and a good visual molecular model for vapor pressure. Here we go.
If you take water in a container and you allow it to start evaporating, the space above the surface of the water will start getting water molecules. That means it's a gas now, and gases impart pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away. So if you put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back in. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container, and that pressure is called the vapor pressure of that liquid. In the case of water, you would say it's the vapor pressure of water. It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happening, but in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate, so there's no net change, but you have established what we call a vapor pressure. And that's hopefully a little bit more of a handle for you on what vapor pressure is. We have other things to tell you later about vapor pressure in other videos.
All right, we're back in our ebook, section 8.3, page 486, looking at this section titled Vapor Pressure. We're going to look at these curves first. These are Maxwell-Boltzmann distribution curves representing the distribution of molecules at a variety of kinetic energies. We know that at a lower temperature, the average kinetic energy of the molecules is lesser than at a higher temperature. Blue curve versus red curve. When the average kinetic energy at a higher temperature increases, because the number of molecules under the curve has to stay the same, as we know from the prior lecture, that not only flattens the curve, it also widens it. And we're seeing that here as we go from blue to red, the flattening and widening of that curve. Meanwhile, you probably also know that below the boiling point of a substance, liquid molecules do turn into a gas phase, create vapor. It's called evaporation. Going from liquid phase to gas phase below the boiling point of a substance is evaporation. If we imagine this dotted line to represent the boiling point of the substance, the minimum kinetic energy that molecules need to escape their intermolecular forces and atmospheric pressure to become a gas, then we can see how a Maxwell-Boltzmann curve establishes that at any given temperature, because that curve goes way out to the right, at any given temperature, there will be some molecules with enough kinetic energy to overcome intermolecular forces and atmospheric pressure and turn into a gas phase. The areas under these curves to the right of the dotted line represent the percentage of molecules, as long as they're at the surface, that can do this. And we can see that at a higher temperature, because the curve flattens and widens, there is a higher percentage of molecules at a greater temperature that will evaporate, that will go from a liquid phase to a gas phase. What that means is that at a higher temperature, there will be greater vapor pressure because there'll be a higher percentage of vapor molecules above the liquid, exerting a higher vapor pressure. This is evidence of that at a higher temperature, the rate of evaporation increases and the vapor pressure above the liquid goes up as well. And as a small side note, if we were to raise the temperature of the substance enough such that the curve were to continue flattening and widening, and the peak of that curve were to be at or to the right of the dotted line, then the average molecules would have enough kinetic energy to overcome intermolecular forces and atmospheric pressure, and that's when we say the substance is at its boiling point. But neither of these are, because the peaks are to the left of the dotted line. So I've scrolled down, I'm on the same page, and I'm looking at this diagram of a gas collection tube apparatus. In an experiment, if a gas is produced, for example, a reaction between zinc and hydrochloric acid producing hydrogen gas and zinc chloride, you want to collect that gas to measure things about it. Measure its volume, its temperature, its pressure, to know other things about it. A common way to do so is to have the reaction happening in a flask, an Erlenmeyer flask. There's a rubber stopper over the top, there's a little hole in the rubber stopper, and there's a tube coming out of it. And that tube is what the gas that is produced comes out of. That tube then can be inserted inside of a bottle that has been pre-filled with water and inverted upside down, kind of like the way a barometer is made. The bottle is completely pre-filled with water, opening in the water, take hand off, and then the water stays up in the top of the bottle. But as the gas is produced and collects in the top of the bottle, that creates pressure that pushes the column of water down. The more that gas is produced, the further the column of water drops. Once enough gas has been produced that the bottle is primarily full of gas, then what is done in an experiment like this is the level of the bottle is adjusted. The bottle is pushed up and down such that the level of the water inside the bottle is equal to the level of the water in the tray. What that does is creates a scenario where, when the level of the water inside is the same as outside, where the pressure inside the bottle must be the same as the pressure outside the bottle. Meaning the pressure of the gases inside the bottle are equal to atmospheric pressure. This is a clever way to know what the pressure is of the gases inside the bottle, because atmospheric pressure can be easily read with a barometer, and if we know that the pressure inside is the same as the pressure outside, we are indirectly getting a measure of the pressure inside because it's equal to atmospheric pressure. Twice, however, I've said gases inside, not gas. A moment ago, I was suggesting that hydrogen gas is produced, leaves the tube, and collects in the bottle. But there's water here down at the bottom of the bottle. Within the bottle, there's water. And water, we know, evaporates, even below its boiling point. The water that evaporates collects in this bottle and is the vapor pressure due to water. So there's not just hydrogen gas, for example, in this bottle. There is some water vapor due to the evaporation that happens that is the water vapor pressure. So again, if we know that the pressure of the gases inside is equal to atmospheric pressure, and let's say that this is a standard pressure day, it's 101.3 kilopascals worth of atmospheric pressure in this room, then the pressure inside is also 101.3 kilopascals. But that's the total pressure, the pressure from the hydrogen gas and the water vapor that evaporated at 25 degrees Celsius. The sum of the water vapor pressure and the pressure from the hydrogen gas is 101.3, Dalton's law of partial pressures. Well, in a moment, we'll see a table that shows us the water vapor pressures at various temperatures. As the temperature goes up, the water vapor pressure goes up, which we saw a bit ago. And at 25 degrees Celsius, the vapor pressure due to water, as long as enough time has elapsed for it to reach equilibrium, is 3.17 kilopascals. So there's 3.17 kilopascals worth of pressure from the water vapor in that bottle. The rest is from hydrogen. So if we do 101.3, the total pressure, minus the vapor pressure due to water, 3.17 kilopascals, that's the pressure of the hydrogen gas in that tube. So we then know the pressure of the hydrogen gas. We might know its volume. We could calculate its moles because we know its temperature. We can do all sorts of great calculations using the ideal gas law. So be aware that whenever there's a problem that involves a gas being collected over water, you've got to always subtract out the vapor pressure due to water from the total pressure to get the pressure of the gas. And we'll do a sample problem involving that in just a little bit. All right, I've flipped my page. I'm on 487 of the ebook now, looking at this section titled Vapor Pressure and Boiling Point. Little highlight in green says every liquid possesses a vapor pressure, which varies by temperature, by the way. The stronger the intermolecular forces between the particles in a liquid, The more strongly they're held together, the less likely evaporation is to occur. The less likely evaporation is to occur, the lower the vapor pressure. Molecules that experience stronger intermolecular forces have lower vapor pressures. Molecules that have weaker intermolecular forces and are more likely to evaporate have higher vapor pressures. We know that molecules with stronger intermolecular forces have higher boiling points, but it's the opposite for vapor pressure. They have lower vapor pressures. Here are, at various temperatures, the vapor pressures from water. At 0 degrees Celsius, water does not evaporate much, only 0.61 kilopascals worth of vapor pressure. But as the temperature goes up, we see the vapor pressure rising. And, not coincidentally, at 100 degrees Celsius, the vapor pressure from water is 101.3 kilopascals. That's the boiling point of water. And from the video we watched, we know that the boiling point of a substance is the point at which the vapor pressure equals atmospheric pressure. And that's why it is standard pressure, 101.3. Still on the same page, just scroll down a little bit, and there's all sorts of great things to discuss about this graph here. The first is that these are three different substances, diethyl ether, ethanol, and water, whose vapor pressures, as the temperature varies, are depicted graphically. Notice that at any given temperature, water, compared to ethanol and diethyl ether, has the lowest vapor pressure. Well, that's because water has stronger intermolecular forces. It has hydrogen bonding. So does ethanol, but ethanol's hydrogen bonding is weaker because there's only one hydrogen bonding region. And then diethyl ether, which is just a polar molecule, has weaker, just regular old dipole-dipole forces. So we're seeing the trend in the strength of intermolecular forces and vapor pressures being depicted here. We're also seeing, as we know, that as the temperature of any substance increases, its vapor pressure also increases. And it's a nonlinear increase. As the temperature goes up, so does the vapor pressure, but it's nonlinear. The final feature of this that's important is the definition, once again, of the boiling point. The boiling point of a substance is the temperature at which the vapor pressure equals the atmospheric pressure. If the boiling points weren't indicated on these curves, they are 34.5 for diethyl ether, 78.5 for ethanol, and 100 for water. We could have figured out what the boiling points of these substances were by finding atmospheric pressure on the y-axis in torr, or in millimeters of mercury at 760, going over to the curve, dropping down to the x-axis, and finding the temperature at which the vapor pressure for that substance equals atmospheric pressure. That's 34.5 for diethyl ether, 78.5 for ethanol, and 100, of course, for water. All right, I flipped the page, looking at this section titled Boiling and Atmospheric Pressure. As we know, there's two factors, primary factors, that influence the boiling point of a substance. One is the atmospheric pressure. The greater the atmospheric pressure, the greater that air is pushing down on a liquid, the harder it is for that liquid to boil, to evaporate. Higher atmospheric pressures result in higher boiling points. At sea level, when pressure is standard, water boils at 100 degrees Celsius. But if you go to the top of Mount Rainier, where the pressure is 500 torr, not 760, water boils at 86 degrees Celsius. It's easier for those liquid molecules to escape their fixed intermolecular forces and the now weaker atmospheric pressure, and they can more readily evaporate and boil. At the top of Mount Everest, almost 30,000 feet tall, water boils at 70 degrees Celsius. So atmospheric pressure influences the temperature at which a substance boils. The lower the pressure, the lower the boiling point. And as we've heard a few times, intermolecular forces also influences vapor pressure and boiling point. The stronger the intermolecular forces, the lower the vapor pressure and boiling point. Mercury, for example, with metallic bonding, not technically an intermolecular force, but a strong attractive force, the strongest on this table, has the lowest vapor pressure and highest boiling point. Diethyl ether, with the weakest intermolecular force, dipole-dipole, has the highest vapor pressure and the lowest boiling point. And then finally, this word volatile or volatility describes how likely a substance will evaporate. Substances with weak intermolecular forces, with high vapor pressures, are more likely to evaporate and are considered to be volatile. All right, I flipped my page. I'm on 490 of the ebook, looking at the section titled Dalton's Law of Partial Pressures, seeing once again this diagram of how a gas can be collected in a gas collection tube, and that gas collection tube won't just have that gas in it, but some water vapor as well. We're going to solve a problem here involving a setup like this. And then a reminder once again of Dalton's law of partial pressures, which is that the total pressure of a mixture of gases is equal to the sum of the partial pressures of each of the gases in that mixture. All right, so we're going to solve a problem, and that will wrap up our lecture today. All right, I'm in 492 of the ebook, looking at practice problem 1 here at the bottom of this page. So I'm going to copy and paste this into a whiteboard, and we'll solve it together. All right, here we go. Lots going on in this problem. We got a 0.65 gram sample of zinc reacting in excess sulfuric acid. Doesn't say that, but that's presumptive, to produce zinc sulfate and hydrogen gas. The hydrogen gas is collected over water, as shown in the diagram. The pressure in the lab, so atmospheric pressure in the lab, is 101.3 kilopascals. The temperature of the gas collected / the water / the room is 20 degrees Celsius. We want to find the volume. It's looking like we'll use the ideal gas law for this. There's pressures involved, there's volumes involved, there's temperatures involved, so PV and RT will come into play. Let's write that out first. All right, there it is. PV equals nRT. So we're given the pressure in the problem, but that's atmospheric pressure. It's not the pressure of the hydrogen gas. Remember, atmospheric pressure is equal to the pressure of the hydrogen gas in this gas collection tube and the vapor pressure due to water. So at some point, we're going to subtract away from 101.3 the total pressure in the cylinder, the vapor pressure due to water at 20, and that'll be the pressure of the gas. So we can get the pressure of the gas. We're trying to find the volume. We don't know how many moles of gas there is. Let's talk about that in a moment. R is a constant, and the temperature is at 20 degrees Celsius. So what we'll do first is write the balanced equation between zinc and sulfuric acid and use some stoichiometry to go from 0.5 grams of zinc to the moles of hydrogen gas produced, which we can then plug into PV and RT and ultimately find V. So let's do that first. Write the balanced equation between zinc and zinc and sulfuric acid. Find how many moles of hydrogen are produced. So I got Zn plus 2 HCl's yields hydrogen gas. It's diatomic, of course, and zinc chloride. I then took 0.65 grams of zinc, divided it by its molar mass to get moles of zinc. And then with a 1-to-1 mole ratio between zinc and hydrogen, which I've got here, that gives me 0.00994 moles of hydrogen. So that's going to go up here into N. Next thing we need to do is figure out what the pressure is from just the hydrogen gas. We know the total pressure in the gas collection tube, once again, is equal to atmospheric pressure, which is 101.3. But that's equal to the pressure of the hydrogen gas plus the partial pressure from water. Well, we don't know the pressure of hydrogen gas, but we do know from our book, from page 479 of the actual book, that at 20 degrees Celsius, the vapor pressure is 2.34 kilopascals. 2.34 kilopascals. So that goes into vapor pressure of water. So we do 101.3 minus 2.34, and that'll be the pressure of just the hydrogen gas. And that's going to be 99 or 99.0 kPa. So we now have our pressure, 99. We're going to find volume. We have our moles, 0.00994. R is R. And the temperature is 20 degrees Celsius, which, of course, we will convert to Kelvin before we plug it in. So let's do that. So there's everything plugged in. 99 kilopascals for pressure, V for volume, 0.0094 moles. The R I used, of course, had to have the pressure unit that agrees with kilopascals, so that's 8.314 kilopascals liters over moles Kelvin. And then this is me converting 20 Celsius to Kelvin, so that's going to be 298 over there. And when we isolate and solve for V, we get 0.23 liters. So that's our final answer. That is the end of our time together today. Enjoy yourselves with whatever it is that's in front of you. Work hard. Make the world a better place.